Ladies and gentlemen, welcome to video lecture number 11 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed last year at the end of 2017 at the Bibliothèque Nationale de France in Paris. Today is now November 14th in the year 2018, and we deal in video number 11 with two sections of the second part of this book, which relate to observational evidence of icosahedral symmetry in the Sun's interior. Second part of this investigation about the presence or not of a so-called solid body vertex at a radial fraction of 0.655, a fraction of the solar photospheric radius. We investigate the location of the relevant parameters, physical parameters inside the Sun between a core which ends, as we saw in video number 10, at 0.31 radius fraction of the photospheric radius in the Sun, and this photospheric surface. The contents of video 11, we start with a recap of video 8 and video 9, in which we found and reported the radial fractions to be checked in the solar interior, as in case of the presence of icosahedral fivefold symmetry in this ball, the central cavity at this ending at this depth, and the presence of an outward boundary of an envelope for this core at this depth. Now we look again at the suggested arrangement. In 3D, this arrangement is, as you remember, like this. And we can see in this cross-section with this cut, which has no physical meaning, but in perspective allows us to imagine a line passing through each of the centers of the 12 balls that compose this arrangement. You see this glass cut approximately shows you by an effect of perspective where such a line, and in fact such a spherical shell, would pass through each of the centers of the 12 balls. This is a 2D projection which was introduced in video 11, in which there are only 4 balls, the centers of which are in the plane of the sheet of the screen or of a paper sheet on which such a drawing is laid. These 4 balls are the 2 polar balls, this ball and this ball. The 2 sets of 2 other balls are in different planes, obviously. Now we have seen in video 10 this dotted line or dashed line, a circle, which represents the dimension of the suggested icosahedral cavity at 0.31 radius fraction of the radius of the overall sphere here. And now in orange we have in color the dotted circle, which represents what was shown in 3D in perspective only as a glass cut through the centers of each of the 12 balls. This was called in part 1 of the Fivefold Sun book, shown in an earlier video, the solid body vertex shell inside a spheroid like the solar ball. This is called a solid body vertex because it is suggested that it is the dividing line, the dividing spherical shell inward of which starts a rigid rotation, solid body rotation in the solar ball. And it is called a vertex because each of the centers which define this spherical shell, ball center, coincides with the vertex of a so-called basic icosahedron, the vertices of which are in each of the 12 balls. The main notions that are found in solar physics literature about the presence of a dividing shell between an exterior envelope and an interior envelope about the solar core are as follows. It is accepted main finding that the fully convective zone in the solar ball starts at about 0.71 radius fraction of the photospheric radius. It is accepted that it is certain that it is more than 0.710 and less than 0.720. More controversial is the idea, not the observational finding, of a sharp transition layer with a width of 0.01 radius fraction, for instance, at about 0.69 radius fraction of the photospheric radius, i.e. Slightly below the depth at which the energy transfer in the sun is found to be fully convective. This idea was formulated in the 80s, in the last century, as a tachocline, a word coming from the terrestrial notion of a thermocline, which is a layer of a sharp transition in temperature in the Earth's surface ocean. In an annex to part 2 with 74 pages, we call this notion an indeterminate marker because it is found in the last few years that in fact the models that arrive at such a sharp transition are fits of functions which somehow are ad hoc functions. We do not find, as we will show in the following, much hard observational evidence of such a transition. Then there is in the literature this very important notion of an anomaly somewhere between 0.6 and 0.7 radius fractions of the solar ball. An anomaly seen as the graphs, which represent the relevant investigation, as a bump in these graphs, which denotes a discrepancy between the predicted values in sound speed with the standard solar physical model and also with many alternative models, which cannot so far be explained. The anomaly is pervasive. The question that is not completely answered is where is located radially the peak of the anomaly, and we'll deal with this now. Finally, there is no explicit mention of any transition in the solar ball near 0.655 radius fraction as predicted by an icosahedral arrangement, whereas in the case of the solar core, it is very well known that the radius of this core is not much different from 0.3 or perhaps 0.31 radius fraction as predicted by icosahedral symmetry. In this work, we start with a methodology that is incremental to what is found in solar physics literature, which is to elucidate a detailed transition path outward of the radiative zone into the convective zone, moving from the center outward. We do not retain a geocentric model, For example, using the metaphor of a terrestrial ocean, solar physics observations have proven that there is no Taylor columns in the solar ball, not in its convective zone, as was expected from a geocentric point of view, transferring the Taylor-Proudman model of the terrestrial ocean onto the Sun. And also likely there is no thermocline or tachocline in the solar convective zone. We consider that 0.71 radius fraction is the start going outward of the fully convective region, but we now want to ask where is the start of the fully radiative region going inward. And in between, we would like to know where is the sharpest gradient in the transition, and this transition probably is much wider in radial depth than 0.01, and maybe it's more than 0.1, as we shall see. That is 10% of the radius of the Sun. A metaphoric model is proposed, the waterfall model, but we do not want to replace a terrestrial metaphor of an ocean by a terrestrial metaphor of a river. This is now a purely illustrative graphic reference, not a physical one. You will see in the next pages what the waterfall refers to. And finally, from a methodological point of view, we want to know what is exactly this anomaly in sound speed models? Is it not a revealing piece of data? We ask where the anomaly in sound speed models is peaking. It's peaking at the predicted icosahedral, the predicted depth of a remarkable shell according to the icosahedral fivefold model. This is found in this section of part 2 of the book, The Fivefold Sun. This is, as you see from the numbering, only one of the several chapters in which this anomaly is discussed and investigated in depth in this book. Now we go back to differential rotation, which was already in the early videos of this series of video lectures. In this figure we see, according to radius in the Sun, the latitudinal rotation curves, which show us that in this blue line, which is at 0.71 radius fraction, which is the accepted start of the fully convective zone in the Sun, this rectangle and this small rectangle here show you that we are already way into a differential rotation zone. So how is it possible that we are in a highly differential rotation zone if we are not in a convective zone? This is impossible physically if we are in a rigid rotation zone by definition, which accompanies the radiative transfer of energy inward of the convective zone. But here on this orange line we see the radius fraction of 0.65 radius fraction of the photospheric solar radius, and we see that it is very close to where these latitudinal differential rotation curves start to diverge, going outward from the center of the Sun. And we also saw in part 1 this close-up, which shows that we are very much within uncertainties at this predicted depth. Now, if we look at not differential rotation in the Sun, but absolute sound speed changes with radius in the Sun, we have here a faint blue line that you can see here, which is at 0.71 radius fraction. which should be where we have a large change occurring, but this is not the case. The change ends at about 0.73 and starts somewhere inward or of or at 0.65 radius fraction. This plot is reconstructed from 3 different plots published by 3 different teams with 3 different methods, and they are plotted together from their data points jointly here with the same scale. And we shall see now in this close-up that there are in fact 2 inflection points that are remarkable in this curve. This one, which marks the bottom of the transition in sound speed change along the solar radius, and it's located at about 0.73 radius fraction. And this one, which is located at the start going from the center outward of this transition in sound speed, and is located near 0.65 radius fraction. This is what we may venture to call a waterfall model. You imagine the water coming from the origin of the river flow, here the waterfall, and here it bottoms out. So we can infer or interpret this situation as the fact that we start at 0.71 or 7.3 actually to be in the fully convective zone, but we remain in a radiative zone outward to 0.65 or 0.655 radius fraction. And then there is a transition of about 0.05 or 0.06 radius fraction percent of the solar radius, over which there is this transition in sound speed. There is also in the earlier graphs a transition that can be glimpsed in differential rotation rate. Now we can show the results of the investigation of more physical variables from an in-depth meta-analysis performed in this work. The first finding historically in this direction was by the Californian US astronomer Campbell as early as 1923, which was in theory made rigorously analyzed by the Dutch researcher van der Holst in 1950. And we have now various Russian teams that focus on this matter. It shows you that between the center of the North Polar Ball and the center of the South Polar Ball, in which is predicted a fraction of the solar diameter of 0.655, or a fraction of a radial fraction of the same value. These authors have found similar or almost exactly identical percentage length of the solar radius for the length of the axial magnetic dipole of the Sun. This is a long story that cannot be recounted here. You see in the book, The Fivefold Sun, it goes over 132 pages. But let us shortly say that these authors found this result from considering the inclination of the magnetic polar plumes about the solar corona from emerging from the solar poles during total solar eclipses from 19 or somewhat earlier before 1900 to present, and the results are consistent across eclipses over time. This can be performed only at minimum epoch eclipses, because around maximum epochs there is no actual dipole. Now this is a list of the other physical variables that were investigated in this project, the Fivefold Sun project. We find, you see, underlined in color, always the same values from about 0.64 to about 0.655, which represent a wide array of physical variations across the solar radius in physical quantities: absolute angular velocity, latitudinal rotation gradient we already cited, time variation of solar interior velocity parameters, various such parameters, the anomaly in sound speed we already cited, density in the solar ball across the solar radius, convective stability across the solar radius, asphericity in the solar ball, pressure scale height in the solar ball, and the location of the onset of lithium depletion. I assert these values, but the authors did not necessarily extract these values explicitly from their data. Now we go to assertions, explicit assertions by authors. So before this century, we have the van der Hulst depth of effective poles of the solar dipoles, which here we equate with the centers of the north polar and south polar outer balls in the suggested fivefold arrangement. In the 1990s, Belvedere and collaborators who found a boundary at this depth for the rigid rotation rate. And we will see in the next page, in this century, how many authors have found a similar depth for a dividing shell in the solar ball. We see, looking at the milestones in the history of the determination of the inward boundary of the Sun's convective zone, that historically we've been going deeper and deeper. So the finding here of a somehow convective zone that is not from the start fully convective, but is not a radiative region at 0.65 radius fraction, is in the timeline of this trend. You see, it was only in 1957 that it was realized that the convective zone is external to the radiative zone, and a radius, a depth of 0.86 only was proposed by the discoverers of this outer envelope. Then we move and move and move to deeper and deeper and deeper evaluations. So the bottom line is that in this investigation, the presence of two radial fractions in the solar ball at 0.310 and at 0.655 radius fraction of the solar photospheric radius, as predicted in the suggested 12-ball icosahedral arrangement, is not falsified by observations, although observations do not suffice, as is the case of the core, to prove that these dividing shells are exactly at the predicted locations. But the suggestion is not falsified. The physical interpretation is that the energy-generating core coincides with the cavity at the center of the 12-ball arrangement, and as far as each of the 12 outer balls is concerned, that first, from its center inward, it coincides with the fully radiative zone, which coincides with the zone of fully rigid rotation. Whereas, secondly, from its center outward in each of the 12 outer balls, this coincides with the partly and only then more outward fully convective zone, whereas the entire region outward of the center is fully differential in its rotation. This is now, ladies and gentlemen, the end of video 11 and of the investigation of radial evidence for or against the presence of icosahedral fivefold symmetry in the solar ball. In the next video, we shall investigate such latitudinal evidence. Thank you for your attention.